Good morning. How's everyone today? So yesterday, I let me see, is the volume okay? Yeah, okay. Yesterday, I was thinking about adding a sorted map to my collection, collection library, which only has the skew and the stack so far. So as the next one, I was thinking of implementing that, a sorted array map, or some sort of sorted map anyways. This guy does it based on an array. This other guy does it based on just a linked tree. And I was hesitating because I had an inkling that the built-in map in JavaScript was already pretty much optimized and would be more performant than these two implementations based on a binary search tree. And I did some tests yesterday, and um, it turns out that for setting and getting from map, the built-in map is much faster than at least those other two implementations, which made me think, then why are people even bothering with them? So I did a quick Google search, and this article sums up some of the stuff that I have found, right? Advantages of binary search tree over hash table. Why would you use them? Um, and basically, and this made a lot of sense. It says we can get all keys in sorted array by just doing in-order traversal of BST. This is not a natural operation in hash tables and requires extra effort. So I thought, yeah, that's true, right? And there are cases where you would want that. And I didn't test for that. I didn't test for traversal. Uh, so maybe I was a little unfair to to sorted maps. And another thing it says is doing order statistics, finding closest lower and greater elements. Now that's interesting, right? Doing range queries, I didn't think about that, but that is totally true. I can see a proper implementation of a binary search tree being faster than a hash table for that. Um, like sorting, these operations are not a natural operation with the hash tables. So that made a lot of sense to me. BSTs are easy to implement. Yeah, okay, whatever. With self-balancing BSTs, all operations are guaranteed to work in O log n time. But with hashing, it's constant at time, but it's average, and some particular operations may be costly. I'm not too worried about that with the built-in map in JavaScript because it's super optimized. I think they have really narrowed down the cases where this actually happens. Still, though, it's interesting. And here's a distinction: self-balancing binary search trees. I am pretty sure that both of the implementations I am testing, and they're the two best ones I could find, right? Most popular and actually used by JS developers. They're just straight binary search trees. So there might be a way to optimize this even more to get better performance out of those implementations if they were implemented as self-balancing binary search trees like red-black trees or what is it called? AVL trees, I think, or splay trees or whatever. So I thought, okay, let's revisit this before I just completely throw away the possibility of implementing my own sorted map. Let's test what BSTs are supposed to be better at than than straight hash tables and see if we can beat the built-in JavaScript implementation. So one of the things I was thinking of doing was testing getting ranges, doing range queries. And oddly enough, well, this implementation here doesn't have an easy method to do that, which was odd to me, because if that is one of the strengths of a binary search tree backed map, why wouldn't you, why wouldn't you have that? So I don't know. So I'm not gonna be able to test that with this implementation. The other one, which is based on an array. Let me just check something here. Does he implement another kind of sorted map? Yeah, he does have a sorted map backed by a sorted set. It'd be interesting to add this to our tests as well. I think I will. Just see which one performs better in different situations. But in any case, if we look at this, I couldn't find a method, and this guy's got a really wide API. It's like, I couldn't find a method to find range, a range of values of keys. But he did implement a filter, I think I saw somewhere. Filter, yeah. Filter returns an array with each value from this collection that passes the given test. Oh. So is it a test? Is it a test on the value or on the key? Because if it's on the value, then that's not going to help. Let's look at the function signature, callback. Yeah, and what does the callback take in terms of parameters? Returns an array with each value from this given test. The given callback receives the value for each entry, the key or index, and the collection itself. If the return value of the callback is truthy, the value. Okay, so we can. It would have been nice to show that here. The index of the value will be ignored, and the resulting array will be compact. What if the return value of the callback is truthy? The value will be included. The index of the value will be ignored, and the resulting array will be compact, even if this collection is an array with holes. Positions in this array. Yeah. Okay, I think I understand. So we could test that, I think. Let's take a look at the sorted map itself, see if it has the filter as well. It'll also return an array. Okay, so we might be able to test this collection here, this implementation, but this one we won't be able to test for finding ranges. But before that, there might be an easier test that we could do, right? It does talk about finding closest, lower, and greater elements. That too, for some reason, both of these do not implement that, which is odd, right? If it's one of the strength of the BST. But they do implement returning the max and the min, right? So that's interesting. I thought we could start there. I have a feeling that is usually something that the BS tree should be faster than just a hash table, right? So let's do that. First, I would like to add a map 5. That's going to be sorted map. And I'm going to get that from, is that the one I'm looking for? Yes, it is. Let's get this guy here. Like that. Sorry. Then I need to add this here. So we're going to call this sorted map. Sorted map. And I need to change this to map 5. Okay. And that is that for the sets. Now the gets. Sorted map. Sorted map. Map 5. Okay. Let's run this, make sure I didn't screw up anything. Right now I think I've got, I'm testing 100,000. 100,000. Yep. Wait, does Node support that? Let's see. No, it doesn't. Bummer. So let's use this. 100,000 would be that, right? This should also be. Do I want this to be to match the? Yeah, logically I would want it to match this number of items. Or do you want it to? Yeah, because then there's going to be a lot of collisions. So let's make it times 10, maybe. Yeah. Let's try that again. Come on. Okay. How interesting. So we see that the sorted array map is like super slow compared to the rest of them. Sorted map does much better, but is still much slower than the BS3 implementation. And the built-in map, built-in, 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 built-in. Built-in map is at least twice as fast as our implementation here for setting. Now for getting, yeah, that's interesting. For getting, the array map is much faster than the just sorted map. But both of them are quite a bit slower than the BS3. And the built-in map is way faster for getting, which you would expect, right? Using a hash table. Now, let's test. What did we want to test? We wanted to test the getting, no, not the getting, but the getting, yeah, the minimum and maximum. Let me separate this so it looks a little bit better on screen. I'm going to just console log a, let's just make it an empty, whoops, the other way around, isn't it? Yeah, an empty line right there. And another one right here. And then we can do min-max. Or I can actually do this, min-max, and an empty line. And I'll do this here too. Get and an empty line. And we'll start with console log. And this will be set. And I don't really need an empty line here. Oh, actually, that is not, it's the opposite that I want. I want the empty line first. There we go. Like that. And here I don't really need to do it. Okay. Nice, this will be cleaner. So let's see. What if we want to get, well, we want to get map1 dot, what is it called? Min returns the smallest value in this collection. And max, okay. Min, boom, map1 dot max, boom. Should I actually console log these? Could be interesting, just to make sure that we have the right, nah, I'll just dirty my code. Would be interesting though, just to make sure. Let's run Quokka. See what we get. Oof, Quokka's gonna be slow though. Might not be a good idea. Might not be a good idea. Okay. Compare that to map5 dot min and map5 max. And then map2. What does he use in terms of API for this? Let's see. Add, clear, is empty, size, contain, search, remove, traversal stuff, minimum and maximum. Okay. Minimum. And map2 dot maximum. Test run failure. File performance has invalid syntax. No, it does not. Oh, okay. Okay, and now here's the interesting part. How do I do that with my built-in map? It doesn't have a min or max, as far as I know. Let's look it up just to be sure. MDN map. Doesn't have much. It has get, has, keys, set, values, which is a method returns a new iterator. So that is what we're going to have to get to do. we're going to have to iterate. Entries method returns a new object that contains the key value pairs, and this iterates over, it contains the values, and this is method returns a new iterator that contains the keys. Cool. So that's what we're going to need to do. We're going to need to map.keys, then iterator.next. Can I use the iterator on the for loop? Can I just feed the iterator to the for loop? Does that work? I don't know. Maybe, maybe not. Oh, this sucks. These guys don't return the index, they return the value. So I won't be able to test what I wanted to test. That is kind of a weird thing. Yeah, smallest value in the collection. Interesting. Yeah. So, we can forget about these. But this one does what we expect it to. So that's good. Now we still have to figure out how to do map 3. If I do, let's say entries, I've got an iterable iterator. Entries or just the keys maybe? Is there a keys? Keys, yeah, that's all we care about right now. Keys. Can I actually loop let key, or actually const key of, would that work? I think it would. I think it would. What if I was to oh no, that's gonna, no. That's just gonna kill Quokka. Probably shouldn't do that. Okay, you know what? Just for the sake of the testing all this, let's make it much smaller. Sets of tens. There we go. So yeah, it works. It's returning the keys. As we can see, 14 is the smallest one, 97 is the highest one. Now, what would be a performant way to do this with the built-in map? Well, before performant, let's try easy. So here's what I would do if all I cared about was making it easy for me to do it. I would just make this an array and whoop, why doesn't that work? Expression expected. Can't I convert a map to an array using the spread operator? I should be able to. Doesn't it? Let's see here. If I go to map, map object holds the key value pairs and remembers them. Okay, iterable. Are we saying a map is initerable and thus can be directly iterated, whereas so it should be able to, I should be able to use the spread operator in that thing. It seems like it won't let me. It's interesting. Why won't you let me? Let's try it some other way. Array from pass in map 3. All right, doesn't complain here. Interesting. Look at what we get. Ah, man, doesn't keep the keys. Of course. So I have to do from map 3 dot keys. Oh, then this is probably going to work, right? If I do it that way. No. Let's see if I do this, and map keys, there's a function call, spread operator. Okay, I think it just doesn't like spread operators. Why? Node is compatible with it. Node 10 point something, whatever. Okay, fine. Let's get back to our array. From, don't want to spend the time to figure out why it's not working. Oh, that's interesting. Huh. Isn't map 3, am I? Yeah, it's the new map. And it says it's an empty array. This is returning an iterable iterator. So why? Hold on. Not entries, keys. It's an iterator. If I do entries, same thing. If I just do map 3, it's just going to use the values. Alright, looks like I don't have a choice to use a for loop. And I was thinking of just using the math.mdn math.max and min, which, you know, would be easier. Can I give it an array? Saying I should be able to use the spread operator to unpack that. That'd be cool. Wait, is the 1, 2, 3 foo equals 1, 2, 3 and const bar equals a new array with foo. Okay, so that works. Okay, I guess it just wasn't. It's because the map, it's considered an iterator, not an iterable. Getcha. That's why it wasn't working. So, what's our workaround? Well, we can do for const index of, or let's just call it key of map3 dot keys, because we know that works. Then we'll push that to an array. I guess we'll push each key to an array. So we'll call that keys, an empty array. Then we'll, push it. So keys dot push key. Oh, that's not the most performant way though, but yeah, whatever. Who cares for now? Let's just then we would simply do math.min and pass in the keys like that. And we should get the same value. There we go. And we can do the same thing with max. 2589, 2589. Good. Okay, so that works. The thing is, how fast is it? And that's what we're going to check. That's what we're interested in. So, console. Okay, let's forget about Quokka for now. Dot time. We're going to call this. That's the BS tree. KV min-max. Min-max. Okay. Min-max time end. And now we're going to do. Now I'm wondering if. Should I, to be fair, to have a fair comparison, should I do this twice? Once for the min, once for the max? Because I'm kind of reusing it now. Because it's a necessary operation to do if you want to find the min or if you want to find the max. Now, it would be reasonable that if you were going to use the map, the built-in map, and wanted to have a way to find the minimum and the maximum, that you would no, you probably would have to. Yeah, I'm gonna do it twice. I'm gonna do it twice. So keys 1 and keys 2, because I think that's what you would need to do. Keys 2. And then you get them from keys 1, you get them from keys 2. Let's try that. Console.time. What did I built, whoops, I need a string. So built in map min max time end built in map min max. All right. Let's give that a try. Oh, I've got it with 10. Let's use, let's use our 100,000 example. Or maybe just a little less than that. Let's just make it 1,000 to start with. Well, that was fast. All right, so set. We already know that the fastest by far is the built-in map. Get, same thing. Now min-max. Well, look at that. Right? So our BS tree is faster. And what if I was just going to use the same one? Would it make a huge difference? Well, cuts it down almost in half. Makes sense, right? Now let's try it with a bigger number. Let's go with our 100,000 from before. Come on, you can do this. Now's a good time to drink some water. Okay, we already know this. This isn't surprising to us. Okay. Oh, wow. Much faster. So this is pretty much 113, 136. So this is pretty much constant time operation here for the BS tree implementation, and we can clearly see that it's not the case for what we're doing here. And that's kind of normal because we're iterating through the entire map. But we can probably make this a little bit better because we're probably, like, I don't know how math.min and max work, under the hood, but we're probably doing work twice here. So let's do this by hand. We will use this here. Hold on. We'll basically do some kind of a reduce. We'll call this min. And again, that's kind of going to be cheating. But actually, this should be, let's see, infinity. And we'll make, what's that, max equal minus infinity. Okay. Yeah, they really should be separate. They really should be separate. I'm not going to need this anymore. They should be separate operations. We'll start with the min, so const key, if, so it's a simple if key is smaller than min. Oh, it's kind of a dumb implementation, right? Because we're using numbers. It would be more complicated. We'd need like a compare function or something. But anyways, for now, it'll serve our purpose. So if key is smaller than min, then min equals key. Simple as that. That's the only thing we need to do. And essentially the same thing here for max. So if key is bigger than max, then max is equal to key. Cool. Good stuff. Let's test that this is doing what we think it's supposed to be doing. Let's go back to our example with 10 items, and let's do min and max and run quokka. Right, got this as a const. Nut. Okay. 1892, 1892. Looks like we got it right. Let's add just a few more numbers in there. 10, 988, and 10, 988. Okay. So this works. Let's stop this. Back to our terminal. Get rid of this here. Yeah. And let's... Did I miss something? I don't think so. Let's just run it. Let's run it and see. Ah. Got to do it with the 5, I think it was. 100,000 items. I have a feeling it'll be faster than what we had done before, but still not nearly as fast as the binary search tree. Which is interesting to me. How does it, like, I can see the binary search tree being super fast for getting the lowest. How does it, wait, where would the lowest number be? Oh yeah, the lowest number would automatically be the deepest number to the left, and the deepest to the right would be the highest one. So yeah, it's just a matter of going straight there. Okay, let's compare. 11 seconds now compared to, that's the one before that. Oh, the other way of doing it was actually faster. What do you know? Interesting. 136. This one took a little longer here too. That's interesting. Curious, I'm going to run it again. Yeah, it's about the same for this one. This one's a little faster here. Interesting. But anyways, I think it's pretty conclusive that for getting a max and a min, the BS tree implementation here is much faster. Now, if we look at what were the other things that the BS tree was supposed to be? Okay, so see that's too bad because but there is something that we could test, and that is iterating in order. I think they both implement that, right? Let's see. Delete values entry at each iterator, every value in this collection. No, not exactly what we want. Aggregates every value. Could have used a reduce to test the min-max thing. But I'm pretty sure it would have been slower, so. Sum, every, any, all, sorted. Returns a sorted array of the values in this collection. Reversed, join, sum, average. Enumerate. That's not what we want, though. Doesn't look like there is. There's an iterator, but we don't know in what order. Iterates every value in this collection. Returns an iterator with the version 1 iterator protocol. What's the version 1 iterator? I don't know. It's every value in this collection. Iterates from start to end within a collection. I have no idea. Logically, it would iterate in some sort of order. Which one, though? I could look at the implementation. Actually, I already have it here. Which one is that? Sorted, 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 sorted. Sorted map. Gotta look at iterate. Store.iterate. Ugh, it's inheriting from the other stuff. Okay, never mind that. What do I do? How do I test this? Well, I don't think I can test it the way I want to test it anyways. I'm curious to test the, I know this guy has it, the map 2. He's got, see, in order traversal, executes the provided function once for each element present in this tree in order. And that's a private function. It probably has pre-order and post, yeah, pre-order and post-order. So which one would give us like a sorted transplant? take a look at the source for that. I think post order or pre-order is the one where it would be kind of sorted in the sorted order. I gotta look this up, I can't remember. Pre-order traversal. In order, 1, 2, none of them give us what we want. It would be a breadth first or level order traversal. 1, 2, 3, 4, 5, right? Yeah, 1, 2, 3, 4, 5. That's if it's a wait a minute. But that's a heap. Or not a heap, but the inverse. That's not a binary search tree. In a binary search tree, does it talk about this? This is an example of binary search tree, yeah. Of binary tree, okay. 1, 2, 4, 5, 3, 1, 2, 5, 5, 5. So none of them give us that's interesting. If you do this, that, this, wait. Yeah, in order. In order works. Why does it say that here? That it's not giving us the right one. Right, in order. Traverse the left subtree. Visit the root. Yeah, traverse the right subtree. So I think it's in order. And this guy's got it, so. In order traversal, let's test it. Let's get this a little smaller. Let's get Quokka back in. Callback is not a function. Yeah, you want a callback. Okay. That's going to be our callback. How's that? No, you don't like it? Empty string. Okay. What kind of callback do you want? What are we looking for here? Tell us the signature. iLoop function, any. That doesn't tell me anything. Let's look here. In order traversal, in order traversal. No, that's the private. What the public one is probably, oh, okay. Util iLoop function v. Oh man, it's just giving us the value. No. Okay, easy fix. Easy fix. We're going to make our keys and our values the same. Let's get this here. Call this Random. Okay. You'll be random. And you'll also be random. There we go. And now this is the value. And we just want to console log the value, please. Interesting that we get an undefined. We get an undefined and that what? We get an undefined, 3 dashes, and then a bunch of numbers. Huh. I gotta see here if map 3. Nope. I don't see any undefined. 55 maps to 55, totals to 12, 80 to 80. We got it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. They're all there. What is this all about? No idea. No idea. Interesting though. Does he say anything about this in there? Executes, which one is it? Executes the provided function once for each element present in this tree in order. It is invoked with one argument, the element value. To break the iteration, you can optionally return false. Mm-hmm. That's, I don't know if this is, that's weird. That's really weird. What if I only add like one element in here? What would you give me? Still go with that undefined thing. Odd. Super odd. Hmm. Yeah. Don't know. But for performance testing, it doesn't really matter. So let's just keep going. Now, so we know how to test this. This is pretty easy. Now we don't actually want to do anything with it, so let's just... Oh. Whoa. The undefined thing went away. What? If I do map 3... Okay, probably just a glitch with Quokka or something. Interesting. Very interesting. Okay. Let's worry about getting our map 3 to... How are we going to do this? We actually have to convert it to an array and then sort it, or implement our own kind of sorting algorithm on it. can't believe that why? Let's see, const map equals, here's our array. We go map 3. Okay, so now it's working. I swear it wasn't working before. Huh. Oh no, yeah, it was working. It's the problem is that it's using the values. Oh, but now we can do that. Now we can do that. But that's kind of cheating, so I'm not going to do it. Okay. So let's worry about sorting. Well, actually, this guy's doing it too. So for this case, we're going to do it. So let's just get take this, put it here. This will be called actually, it makes more sense to have this under here. Don't know why I didn't do it that way. Before, be a space here, space there. Okay. Set, get, min max. It's a lot of work just to figure out if it's worth trying to do this. But hey, it's for science. Okay. This will be traversal. In order traversal. In order traversal. I guess we can call it. Like this. Okay, now we test this one first. Console.log, not log. Time. This is BS tree, KV in order. Just gonna call it that. In order, time, end. Okay. Let's do the same thing here, except this will be built-in map. Okay, and now I need to, okay, I was going to do it that way, right? Map 3, just make it that. Oh, we actually get the key value pairs. Okay. So why wasn't this working before? Strange. Anyways, so now we've got that. We sort it. Boom. And then actually need to traverse it, so dot for each, I guess. would be the equivalent, and then we don't do anything with it. Just like that. But if I was to do something with it, I've got my undefined. Oh, that's because, okay. No, it makes sense. 17, 36, 41. Yeah. It's all working. Okay. But we're going to get rid of these. Just interested in the performance of it. Let's get rid of Quokka. Let's do our little test on, let's go straight for the 100,000 items and hope it doesn't take forever. Well, you know what, just in case. I don't want to be sitting here for half an hour. Let's start with 10,000. We're done? I looked away for a second and it looks like it's done. Well, that was fast, okay. Oh, man, wow, okay, yeah. It looks like it's almost, well, that'll be interesting. Let's compare now with more items. This will take longer though. But I think we have just found a reason to implement some kind of a binary search tree backed collection. Yep. So, okay, that's interesting. The BS tree with 10,000 items, the traversal took 2 seconds. With oh, look at that. That's really interesting. Now look at that first, okay? So with 10,000 items, getting us the minimum and the maximum took 0.18 milliseconds. And wait, 0.18, yeah, okay. And with more, with 100,000 items, it took 0.15 milliseconds. So obviously we're dealing with something that's like pretty much constant time. Now if we're looking at the built-in array, the built-in map, 1.4 milliseconds here, 10 there. So that's O of n, right? We've got 10 times the items. It took 10 times the time to get us the minimum and maximum. Now let's look at the traversal. The BS tree took basically 2 milliseconds, and it took double the time for 10 times the items. So that's like a log of n, something like that, which is pretty good, especially compared to our built-in, what we had to do to get the built-in map sorted. And there, we could have done that, like rolled out our own, because what we're doing here is we're iterating through the entire thing, making an array out of it. Then we're sorting the array, which probably involves some, well, of course, it involves some kind of iteration through the array. So we could have rolled our own sort, like a merge sort or quick sort or whatever, that does that directly on the map, but I'm pretty sure it still would have been slower and quite a bit slower than what we're getting with the binary search tree. Which is pretty cool. Pretty cool. Yeah, because in any case, we still need, and see, that's the thing, and then we iterate through this. So even if we can, get this a little faster, we still have to, once we're done doing that, which requires iterating through the whole thing, we still need to go ahead and iterate through the whole thing. But, okay, so here's the thing. Here's the interesting thing. If we're testing, like, globally, right? Because this makes it obvious that um, for anything that requires iterating through our entire collection in order, in order, right? Then the binary search tree is a big time winner. And the cost for that is that it takes longer to insert, right? To set things. Um, but if we look here, not that much longer. Am I looking at the right one here? Hold on. No, this is the way. Okay. Um, twice as long. Twice as long to insert. And the thing is, usually you'll just insert one thing at a time, right? Not always. There's use cases for populating like an entire tree from like an array or something or whatever. But it's twice as long, but it's way, 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 way faster to iterate after that. And in terms of getting, it's 4 times slow. No, let's look here. It's about 4 times slower getting one item. Of course, it's hard to beat a hash table for that. So it's interesting. It really depends on what you expect to do. And we're not able to test because those implementations don't have a way to find ranges. But I suspect that is one very useful case for binary search trees. And it would, be so much faster than doing it with an array or the built-in map, which would need to be converted to an array anyways to do this, probably. So, interesting. Yeah. So I think it's worth. I think it's worth it. I think it's worth it having some sort of a. I could probably do a sorted map and a sorted set where the keys are the value, right? So I should probably start with the sorted set, I guess. Although the sorted set, how does that work? Can a binary search tree have duplicates? How? That's a good question. Can a BST, well, let's just, okay. Can a binary search tree, oh, well, look at that. I'm not the only dummy that has been searching for this. Handle duplicates in binary search tree. In a binary search tree, all keys in left subtree of a key must be smaller and all keys in right sub must be greater. So binary search tree by definition has distinct keys and duplicates in binary search trees are not allowed. Interesting. So really a binary search tree is kind of a set, right? Well, I guess in a sense a map too, right? If I try to, what would happen if I do? All right, let's bring our friend Quokka back in. Just leave that to small number so that it's going to run. All right, so if I do, let's say we're just going to call this map and initialize a map. Yeah, forgot the new. Thank you. And if I do map.set and I want my key to be 1 and my value to be yo. Okay, cool. And now if we look at our map, it'll have that. Yes. Now if I try to set, oh yeah, that's right. If I just use the same key, it'll just yeah. Yeah. So you can't have duplicate keys. I don't know why I had to test that out. I knew that. Sometimes you just have to. Okay. All right. So where do I start? Where do I start? I could start by making some sort of a base tree class, because a tree would be useful as well. Just like a generic tree would be useful. And once I have that working, I could make a special case of the tree, which is a binary search tree. And I think I might as well, if I'm going to do that, I might as well try to implement like a red and black search tree, or black and red, whatever it's called. Or even better, I think, would be some of the newer ranked search trees like AVL or even WAVL or whatever, if they're not too complicated to implement. So let's start by just a generic tree. Let's do that. Let's try that. Am I keeping this? Do I need to keep this? It was just like experimental stuff, right? I don't think I need to keep it. Famous last words, right? Yeah, okay. Let's save it to Git. Added or add sorted map performance tests. No, we'll say traversal performance tests. There we go. And now we're going to delete it. So that way, if we ever need it in the future. Okay, let's main. Do I need a main? Maybe later. Or more like an index, I guess. Tree.ts. Where do I start? Well, I would need a tree node class. Abstract. Or should I make just, yeah, maybe class tree node. Should I make it a Do I need an interface for this? Should I make an abstract class? There's all kinds of possibilities here. All right, let's just start with a class and we'll see. So our tree node class, We want this to be generic. Let's keep that simple. It's going to have a. Do we want a constructor? Do we want a constructor? It would be useful, no doubt. Constructor. Are we ever going to access? Yeah, we will from the outside of the class. I want the tree node to not have much stuff. We're going to use a tree class to wrap the tree node classes. So basically it's just holding the data and the pointers to children and parent. So we're going to start with a parent. No, I'm going to put that one at the end because it might be optional or null or something if it's the root. We'll see. So how about that? Let's start with do I want it to be read-only? I don't know. Let's make it public. I'm going to need to set that value. Am I going to set that value anywhere but from within the constructor? Should the tree node be immutable? Not sure. So let's make it public. And we're going to call this value or data. Let's call it data. Make it real generic. Data type T, then parent is going to be, no, parent's going to come last. So we're going to have a, what are we going to have now? No, that I definitely don't want to be public. Or at least, let's make it read-only. If I make it read-only though, it's still dangerous. Let's make it private. Private children. Private children. Which is going to be an array of what? An array of tree nodes. Which are going to be of type T. Okay. And now, since it's a tree, only have one parent, which will be, you know what, since I'm not quite sure how I'm going to be dealing with all this yet, I'm going to make everything private for now. Private parent. And that's a type tree node. This. All right. Good. Let's start with that. And now, class tree. Generic type. And this should probably at least implement the collection interface. It'd be logical that all our different kinds of data structures and collections implement our basic functions. Now, I'm not going to make it extend the abstract collection because that is based on the array. So there's really no point in doing that, I think, anyways. But we probably still want to implement the collection interface. What is in our collection interface? Something for the size, something to add, something to clear, something to check if we have something, something to check if it's empty, something to remove an element. This all seems very sensible. And so we shall implement it. We might have some other methods with different names that do different things or the same things, but I think they should all implement at least a collection interface. So, what are we missing here? We are missing size, add, clear, has, blah, blah, blah. Okay. But, so let's say we create a tree. So we go something like, and we want it to be an empty tree. So we go const t equals new tree. And start with it empty. Might get back to the constructor later. So cool, we've got a tree. Now what? What happens when we construct a tree? I think we have to deal with it right now, don't we? Constructor. We could take, what are we doing with, let's see the other ones here. Actually, it would make sense to take an iterable. That'd be pretty cool, right? Save us some time if we did that. Oh, would it make sense though for a generic tree? It wouldn't really make sense. Like I can see for a binary search tree, or even a binary tree. Or even a heap. But just for a base tree, I don't think so. So, we're gonna, construct it always empty. So if that's what we do, then I guess we don't really need a constructor. We can probably, what do we need? We need the root. We need to keep track of the root of our tree. The root of our tree is going to be well, nothing. It starts with nothing. Null, maybe? Or undefined. Normally, it would be of type. Let's type it properly. So it would be of type. Here's an interesting thing. Because a tree node is essentially also a tree in and of itself, right? It's a subtree. Do I want right? Because you could implement just a tree actually with one class. Would we want that? It'd be really flexible in the sense that you can call a bunch of methods on a subtree. But it could also get kind of confusing. They're going to keep it that way. So tree node. Tree node it is. Oh, actually, I could look at how this guy. Let's see here. How does he implement his tree? Does he have just a tree? No, it's just okay. Oh, he's got a BS tree node or null, right? Compare function and elements is probably, I don't know, like the size. Constructor, this root equals null, right? So he had the kind of the same idea that we did. I wonder if we could use like an empty. Let's keep it simple. So we're going to go with that too. I don't see the need to do it in the constructor because we don't have one right now. We're not passing in anything. So okay, we start with this. Now, let's say that we wanted to add something to the tree. Well, here's the thing. In just a generic tree that we could use, for instance, in yeah, we need a way to add. We need a way to add children to a specific node. So can I actually just have All right, I think I need a little bit of inspiration. Let's see, generic tree JavaScript. Generic tree implementation JavaScript. Oh, let's take a look at this. Data, parent, children, root. Oh, this is essentially what I had in mind. Var node equals new node. Data. Okay, so when creating a tree, it makes sense that you're passing in at least the parent node. Then again, maybe not. Add. Okay, this is how he does it. Add child parent. Since every method of a tree requires us to traverse a tree, we will first implement methods that define different types of tree traversal. Yeah, makes sense. I want to see the add. Add data to data traversal. We now have a method to search for a specific node in our tree. Let's now define a method that will enable us to add a node to a specific node. Okay. Do I like that way of doing it? What are my other options? Let's look at some other implementations. General tree data structure in JavaScript. Let's look at this. This guy. Okay, so see, this guy puts the add child on the node object itself. And I think this makes some sense. Because I'm thinking that if you do a search, boom, you're given a node as you're returned a node. Well, really you shouldn't, right? If I do, how do I want this? I don't want to have to deal, if I have a tree, I don't want to have to deal with nodes. I want to have to deal with my collection, and I want to be able to, if I want to, yeah, I got to think about this in a very abstract kind of way. When would I use a tree? Like just a generic tree. I would use it if, yeah, for game playing stuff sometimes. Like implementing a game state tree. Yeah, I have to keep this super generic. That's kind of an interesting question. And it's an important decision because it's going to be quite a bit of work to change my implementation later on if I decide that I want to have to. Well, actually, it shouldn't be that bad. It shouldn't be that bad. Okay, so maybe I'm going to keep. Let's go with the idea that I'm going to keep my tree node class real dumb. And everything's going to be a method on the tree class. Just for reference, though, I should keep this one. Maybe not. See if there's another one, though. Everything I need to know about trees. Cool. Yay, trees, drawings, stuff. Where's the code? Let's go to binary tree. In Python, sure, why not? So we've got value, left child, right child. Well, that's a binary tree, yeah. That's not what I want. I don't want to That's going to be for later. I want just a normal tree. This is a nice little article, though. Might want to keep that on the side here. Let's search for the node value or not. The algorithm that we built, I was about to do search for a given value integer number. We will say it does an important item to note is how we define the tree insertion algorithm. First we have our root node, all the left subtree nodes, blah 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 blah. Yeah. Okay, I'm wondering if I shouldn't just go straight to implementing my binary search tree, or at least a binary tree, and that could inform my decision on how to make my generic tree. I don't know which way would be better. Might need to try some things. Because let's say okay, so if I'm implementing collection, then I need to have a add method, for instance, right? So we're saying, all right, let's add something to our tree. And that something would be some kind of value of type t. But where does it put it in the tree? Do we care where it puts it in the tree? Probably if we're using the tree, not just like, yeah, okay, I see where my problem is. There is a difference between a tree as a simple collection and a tree as a representation of something. For instance, game states in a game of chess or tic-tac-toe or whatever. And they're used very differently. In the one case, you kind of need to tell the tree where to put the new nodes. In the other one, the tree decides for itself where it's going to put the value you're wanting to add. Interesting. Yeah. Okay. I think I'm gonna have to think about this. So would it even make sense to have a base tree class in that case, since they're going to be very different in the way they're going to be used? It's going to require a little bit of thinking. So in this case, if I wanted to implement a binary tree here. Okay, so this could be my base. All right, implement a binary tree. And then I could augment that. Maybe. Maybe I could do that. So let's think about this. Well, in that case, if we do implement a binary tree, we would want a constructor and the possibility of passing in an iterable, well, basically all of this. Something similar to that, anyways. Except we don't have this elements here. So I'm going to need to find an implementation here later on to do implement this. Duh. Okay. Now private root tree node. That's I'm gonna have that here, like that. Now, obviously, if I have a generic binary tree, the collection, so it could end up being a map, it could be a set, it could be, yeah, a map or a set, I guess. So this needs to, this means that T can be just a value, or it could be a key value pair. We don't really care, but we need a way to compare. We need a way to compare. Right. Let's take a look at this here. I think there's a comparer. What is that? The comparer. Provides a base class for implementations with the iCompare generic interface. Derives a class box line first from the comparer. What's the iCompare? Let's take a look at this. Defines a method that a type implements to compare two objects. Yep. Okay. Implements the iCompare interface to compare objects of type box according to their dimensions. That's just an example. Okay, this interface is used with the list.sort and list.binary search. Yeah. It provides a way to customize the sort order of a collection. Classes that implement this interface includes the sorted dictionary, the sorted list, generic classes. Okay. Okay. So that's interesting. Compare two objects, basically. And returns a value indicating whether one is less than, equal to, or greater than the other. What are we returning? A number less than 0, x is less than y. Yeah, I get it. It's like the sort function. So if I look at the actual implementation here, that's not going to tell us much though. Yeah, okay. Should I implement this as a separate class, as a type, because really it's just a function. I don't really need a whole class for that, do I? And the thing is, we should probably pass it in as a in the constructor, right? What uses it again? The sorted dictionary uses it, right? It implements the, it doesn't? Or it inherits from, boy, I thought it did. Didn't it say that? Hmm. Key, typical key, attributes, serializable attribute, implements my collection, my dictionary, my enumerable. I don't see the comparer. Let's look at the methods. Explicit interface implementations. Interesting. Although this is all public stuff, right? So, and I'm guessing the compare thing would be private. Yeah, because you're not actually using it. It's internally. It's being used internally. Oh, properties. Okay. Compare. Gets the I compare used to order the elements of the sorted dictionary. Yes, but where? Oh, is it in the constructor maybe? Constructor. Sorted dictionary. Ah, there we go. So you take in the value and then you take in the I comparer. Oh no, actually, you just take in the compare. Okay, so those are all the options here. Take in just the compare. Take in some kind of iterable, or take in both the iterable and the compare. Ha! Okay. Okay. So let's go with constructor compare. I don't know what the type of that thing is going to be yet. So type compare. It's generic to. So that's an option. And then this is now a binary tree. Would this work? And then I would need no, okay. this is an option, this is an option, and then we have um, iterable, iterable, and compare, compare, that's another option. And then, what are you saying now here? The Silva signature is not compatible with the, oh, yep, we're getting to that. Take a chill pill, constructor, and this is going to be iterable. So this will be the most, oh, I also need an empty constructor if I want to have all my, so constructor empty, constructor with an iterable, constructor with compare, and or an iterable and a compare. So if I do this, iterable, iterable or compare is of type, okay, and it's optional, and it's of type iterable or of type compare. Compare, need my generics in there, okay. Boom, okay, and then this can only be a compare. But it calls it okay. Type compare T. Is that the right way to do it? Iterable, cannot find name iterable. Really? Oh yeah. So you know what? I know that I need to implement this. Let's start by making a interface compare. Might put that in its own class later. So it's a function, so, and it's generic. All right, generic function that takes in, what's the signature here? int? No. What does that mean? int. In. Don't know what that means. All right, let's look at the actual implementation. I think that'll be, there we go. Compare T. But it needs to be, it needs to be a function. All right, it's because it's an object, so this is the actual, that's what we're interested in. There we go. Yeah, let's not make it an object. I mean, it doesn't really need to be. So, interface compare. Maybe. Or maybe just compare func. How's that? I like it. Let's go with that. I guess I should change the name of the variable as well. Compare func. No, I can never remember how to do this. So this should be x of type t, y of type t. You return. Let's make it actually. Should we? Less than 0, 0, greater than 0. Yeah. So I'll just return a number. And I think that's right. What if I was to put the generic here? That's what I never quite remember. This value is never read. Type compare func is not generic. It's not, eh? But it kind of is, though. That's the thing. So what if I was to remove that from here, put that here instead? That would make more sense, right? Oh, look at the time. I guess that's it for me for today. 2 hours go by fast when you're coding. So we're Thursday. Tomorrow I won't be streaming, as is I usually stream on Friday afternoons, but I won't be able to. So I guess I'll see you all next Monday, most likely. Bye-bye.